Welcome back, students. We were discussing oxidation state of actinides. And in case of oxidation state of actinides, we discussed that this is a bit different from lanthanides because the range for oxidation state corresponding to lanthanide was not wide, while in case of actinide, the range is quite wide. Starting from oxidation state plus 2, lanthanides are spread over a range of up to plus 7. So actinide, sorry. In this case, the 3 was common oxidation state for actinides is like lanthanides, just like lanthanides. And after beyond 3, there was also oxidation state plus 4, plus 5, plus 6, and plus 7. We already discussed that why some oxidation state are extra stable than other. So this was on the basis of electrons in the F subshell of the corresponding system. In case of americium, was Y plus 2 was stable, and in case of californium are going to the end of the series. Nobelium was also stable in plus 2 oxidation state. So if you look at the color scheme of the table, so there are two colors in the table. One is black and the other one is red. So red color shows that these oxidation states are stable and they can widely be found in compounds of actinides. Now coming toward actinides contraction is in case of lanthanides, we discussed that steady decrease in uh, size of ion or size of elemental lanthanide was called contraction. In a similar way, in case of actinides, also the steady decrease in ionic radius or elemental radius or atomic radius of actinide is called actinide contraction. Again, this is similar to lanthanides, and steady decrease is observed from one end or left hand side of the series to right hand side of the series. From actinium through lawrencium, the size of the species, the elemental or ions, it decreases, and this phenomena, this situation of steady decrease in size is called actinide contraction. Now this is similar to lanthanides, and this is because of the shielding of one f electrons which enters, and this shielding by this the one f electron by another one is less as compared to the d series or d block elements. Therefore the size does not increase up to larger extent as in D block elements we have observed, or that is the normal phenomena there. But here the decrease is quite steady, and elements are very close to each other in terms of their ionic size or elemental size. Shape of F orbital is also very much diffused, and particularly in case of 5F. So 5F is more diffused as compared to 4F, and this diffusion also caused some difference between the lanthanides and actinides. So in case of lanthanides, the decrease were quite steady. There was regular trend in it decreasing the ionic size of lanthanides, while in case of actinides, there will be some violations. There are some differences. So that can also be explained that 5F is more diffused as compared to 4F. Therefore, these elements are a bit different from lanthanide series. So increase in atomic number by 1 increases, and the effective nuclear charge also is now here effective, and here is operative, and decrease in size is observed, or this decrease in size is caused. It means that when atomic number increases by 1, it means effective nuclear charge also increases, and this increase causes a decrease because mutual attraction between electrons and the nucleus increases, and this mutual attraction between electron and nucleus cause to shrink the overall size, to cause a shrink in overall size or decrease in overall size of the ion. The change is not steady as we discussed. Just like for lanthanides, there are some big jumps, and we are discussing these big jumps in coming slide in the form of graph. And this is due to lesser shielding of 5f electrons comparative to 4f. for lanthanides, and the result is stronger pull by the nucleus. Now, let's graphically represent things. So, for lanthanides, we will for actinides we will consider here metal in plus 3 oxidation state, and for these metal 3 ions, the radius has been measured in picometer. So for actinium, the size which has been experimentally observed for its complexes, and here if you look, I have adopted the data from A.G. Shaw book, which already you have, and for metal complexes bearing coordination number 6. So this data particularly belongs to those complexes where oxidation, the coordination number of complexes is 6. So actinide, in case of plus 3 oxidation state, in and around it there are 6 bonds, or there are 6 ligands. So in case of coordination number 6, it has the ionic radius 111 picometer, and going through the series for californium the size decreases to 95 picometer. Now, this is a steady decrease in the size, but if you look at the line, so the line is not quite steady or quite regular as we discussed or we observed for lanthanide series, and this is because of the nature of the 5f orbital in the shape of the metal ion. This is for plus 3 ions, and if we consider the ionic size of plus 4 ion, so for plus 4 ion the ionic radius further decreases, and it falls for actinium from 101 for metal in plus 3 oxidation state to 99 for its plus 4 oxidation state. And once again, these data has been collected for those species where coordination number of the metal ion is 8, it is not 6, because this in this case in plus 4 oxidation state the metal is too much reactive and it can accommodate up to 8 ligands, while in case of plus 3 oxidation state the metals are not that much reactive as plus 4 is, and in that case only 6 ligands were accommodated by the metal ion. Now the ionic size is 99 picometer, or ionic radii is 99 picometer for actinium, and it decreases up till californium, and it falls to 82 picometer. And if you look once again, the irregularity in the graph is further is less, and these big jumps or big drops, this is because of the nature of 5f orbital for actinides, which was not observed for lanthanides. So this is the data, and overall if we look, so there is steady decrease from 99 to 82 in the series. And one question arises here, that why we have considered actinide complexes from actinium to californium and rest have not been included in the series. We already have discussed the nature of the actinide metals or actinide metal ions, that they are radioactive and they do not freely occur in the nature, because of the reason that they have very short half-life, and due to short half-life they do not exist in the nature. It means after californium the half-life of the metal is too small, and studies in this line, as we discussed for coordination number 6 and 8, it has never been conducted, therefore data is not available for rest of the metal ions. Coming toward some more physical properties, so density of actinides, if we look for thorium, the density is 11.72, and for plutonium it is 19.82, and these two values indicate that the density decreases from thorium to plutonium, because this is 11 and this is 19 gram per cubic centimeter. Then the value drop in the series, and for americium it is again 11.7, and for curium it is 7 gram per centimeter. It means the trend in density of actinide series is once again not regular. There are some drops and some rises in the data, so the density is not regular, and again this is because of the overall volume of the atom, that overall volume some Next is melting point and boiling point of lanthanides. So again, most of the data is not available for all members of the series regarding their melting and boiling points. And for those where the data is available, so the trend is not regular. And here some examples are given for actinium. The melting point is now is 1323 Kelvin, while boiling point has not been determined so far. Then thorium has boiling melting point and boiling point in this range. Protactinium has a melting point known, is boiling point is unknown. For uranium, we have both the values melting point and boiling point. And if you consider the data is not regular, just like density as we discussed here in about topic, there this if we compare their data, so it is 1300, then 2000, so it increases again, it decreases, and for uranium it further drops to 1400. So there is no regular trend, and the difference between 1300 and 20,000 is around about 700 Kelvin, while between these two species, these two members, the difference is only 500 Kelvin, and between these two consecutive species, the difference is 100. So it means, or it indicates, that the trend in melting point is not regular. In case of boiling point, although much of the data is unknown or not reported so far, but if we look at the trend, so melting point was, although there was an increase or decrease in the melting point, but if we compare the boiling points, so thorium has very close boiling point to uranium, that is 4100 and 4000. So there is a difference of, although there is another member in between, that is protactinium, but there is a difference of 100 between these two species. So this data can also not be discussed or explained in full detail as we have discussed data for lanthanide series. Next is magnetic properties, and in case of magnetic properties, again, just like lanthanides, we discussed that unpaired electrons were involved in determination of magnetic properties of lanthanides, and on the basis of unpaired electrons, we were able to design a formula for magnetism, for prediction of magnetism of lanthanide series. And if you remember, there were two factors involved in determination of magnetic properties of actinides. One was spin factor and the other one was orbital factor. So spin, orbit, they both were involved equally in determination of magnetic properties, and the formula was not straightforward as for other elements of the periodic table. In this case, again, the same formula will be used where spin and orbit both are involved in determination of the magnetic properties of actinides. Now, in this case, the orbital where the incoming electrons have been accommodated is 5f, and these electrons are less effectively shielded, and this less effective shielding results in quenching of orbital contribution. So it means if we are determining magnetic properties for lanthanides as well as actinides, and somehow the systems are similar, so what we will find theoretically, the value obtained for lanthanides and actinides should be equal. But if we compare it with actual values or experimental values, so we can find that there will be small difference between experimental and theoretical value of lanthanides, while this difference will be big for actinides, and this is because of quenching of orbital contribution in magnetic properties. So whenever orbital contribution is quenched, it will result into decrease in magnetic properties of actinides.